Right now, as you're listening to this, something is happening that you cannot see, cannot hear, and cannot feel. A single particle, smaller than an atom, is streaking toward Earth from somewhere deep in space. It has been traveling for millions of years, possibly longer. And here's the part that should stop you in your tracks. This one particle, this invisible speck that weighs almost nothing, is carrying more kinetic energy than a baseball thrown across a backyard. A subatomic particle hitting with the force of a macroscopic object. That shouldn't be possible. But it is. And when you understand why, when you understand what these particles actually are and where they come from, it changes how you think about the universe and the violence hiding inside it. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with the name itself, because the name is wrong. Cosmic rays are not rays. That might seem like a strange way to begin, but it matters. Because the name has been misleading people for over a century. When you hear the word ray, you probably think of a beam of light, a laser, a sunbeam streaming through a window, something clean and straight, and made of electromagnetic energy. That is not what a cosmic ray is. A cosmic ray is a physical object. It's a particle, a tiny piece of matter, an actual thing with mass, hurtling through space at nearly the speed of light. Most cosmic rays are protons, bare, stripped down hydrogen nuclei. Just a single proton, no electron orbiting it, no atom surrounding it, just the nucleus itself, flying alone through the vacuum of space at velocities that are almost impossible to comprehend. Some cosmic rays are heavier. They can be the nuclei of helium atoms, which physicists call alpha particles, or they can be the nuclei of heavier elements, carbon, oxygen, iron. These are atoms that have been completely stripped of their electrons by the extreme environments where they were born. What remains is just the nucleus, a tight cluster of protons and neutrons, carrying a positive electric charge and moving through space with extraordinary energy. So when we say cosmic ray, what we really mean is a subatomic bullet. A charged particle launched from somewhere in the universe at a speed so close to the speed of light that the difference is almost unmeasurable. These particles are not beams of light. They are not electromagnetic radiation like radio waves or X-rays or gamma rays. They are physical matter. Tiny, yes. Incredibly small, but real, tangible material objects with mass and momentum and kinetic energy, and sometimes a shocking amount of kinetic energy. The reason we call them rays at all goes back to the early 20th century when scientists first discovered them. In the early 1900s, physicists noticed something puzzling. They had instruments called electroscopes, devices that could detect electric charge in the air. These instruments were slowly losing their charge even when shielded from known radiation sources. Something invisible was ionizing the air around them. At first, scientists assumed this was coming from radioactive elements in the ground. Radioactivity had been discovered only a few years earlier, and the ground does contain naturally radioactive minerals. But then, in 1912, an Austrian physicist named Victor Hess did something remarkably brave. He took his instruments up in a balloon, not a weather balloon, a manned balloon. He personally ascended to altitudes above 5,000 meters, carrying his electroscopes and measuring the ionization of the air at various heights. What he found changed everything. As he went higher, further from the ground and its radioactive rocks, the ionization did not decrease. It increased dramatically. At 5,000 meters, the ionization was several times stronger than at ground level. This made no sense if the source was in the ground. The source had to be coming from above, from space. Hess had discovered that something was streaming in from the cosmos, penetrating the atmosphere and ionizing the air. He described it as a penetrating radiation entering our atmosphere from above. In the 1920s, the American physicist Robert Millikan gave the phenomenon the name that stuck. He called them cosmic rays, and the name held even though further research revealed that these were not rays at all. They were particles. By the 1920s and 30s, physicists had begun to figure out that these so-called rays were actually charged particles, mostly protons, arriving from space with tremendous energy. But by then, the name was already established in scientific literature, in textbooks, in the public imagination. Changing it would have caused confusion. So we kept calling them cosmic rays, even though that name is technically inaccurate. It would be more precise to call them cosmic particles. But science, like language, often keeps its old names long after they have stopped being accurate. Now, let's talk about what makes cosmic rays genuinely extraordinary. Because the truly stunning thing about cosmic rays is not what they are. A proton is a proton. Every hydrogen atom in your body has one. Every star is made mostly of them. What makes cosmic ray protons special is how fast they are moving. Speed changes everything. At everyday speeds, a proton is nothing. It has a mass of about 1.67 times 10 to the negative 27 kilograms. That number is so small, it is essentially meaningless in everyday terms. A proton weighs almost nothing. If you put a trillion protons on a scale, they would weigh less than 2 grams. A single proton is so light that no human scale could ever measure it. And at ordinary speeds, a proton carries almost no energy. If you gently tossed a proton across a room, its kinetic energy would be so small that it could not affect anything. You would never notice it. You could not feel it. It would pass through you without any interaction at all. But cosmic rays are not moving at ordinary speeds. They are moving at nearly the speed of light. And this is where physics becomes strange, because at speeds close to light speed, the relationship between speed and energy is not what your everyday intuition would suggest. At everyday speeds, doubling the velocity of an object quadruples its kinetic energy. That is a basic result from classical physics. A car moving at 60 miles per hour carries 4 times the kinetic energy of the same car moving at 30 miles per hour. This relationship holds perfectly well for baseballs, cars, airplanes, even spacecraft. But it breaks down when you approach the speed of light. As a particle gets closer and closer to light speed, its energy does not just increase, it skyrockets. It climbs not gradually but explosively. A proton moving at 90% of light speed has significant energy. A proton moving at 99% of light speed has much more. A proton moving at 99.9% has enormously more still. And a proton moving at 99.999999999999% of light speed, well, that proton carries energy that belongs in a completely different category. Energy that would seem absurd if you did not understand the physics behind it. This brings us to one of the most astonishing observations in the history of physics. On the evening of October 15th, 1991, a detector at the University of Utah called the Fly's Eye a collection of mirrors and sensors spread across the desert floor designed to detect the faint flashes of light produced when cosmic rays hit the atmosphere, recorded something that should not have been possible. A single particle, a single subatomic particle, struck the upper atmosphere with a kinetic energy of about 50 joules. 50 joules. Let me explain why that number is so shocking. 50 joules is roughly the kinetic energy of a baseball thrown at about 60 miles per hour. It is approximately the energy of a tennis ball served at around 90 miles per hour. It is the amount of energy you would feel if someone dropped a large hardcover book on your foot from the top of a tall bookshelf. These are macroscopic energies. They are energies you can feel with your body, energies that can hurt you, energies that belong to the world of everyday objects. And this was a single proton, one proton, carrying the energy of a thrown baseball. The particle was moving so close to the speed of light that the difference between its speed and true light speed was almost immeasurably small. If you and this particle had a race, and light itself was also in the race, and you watched from the finish line as both the particle and a photon of light traveled across the entire observable universe, the photon would arrive first, but the particle would arrive only a fraction of a second later, not hours later, not minutes later, a fraction of a second, after a journey of over 13 billion years. That is how close to light speed this particle was traveling. Scientists named it the "Oh my God" particle, not an official scientific designation, just a name that came from the genuine shock of the physicist who detected it. Because it defied expectations. It defied what most physicists thought was physically reasonable. A subatomic particle with the kinetic energy of a macroscopic object. Something almost too small to measure, carrying enough energy to physically move things you can see and touch. The "Oh my God" particle was not just an extreme cosmic ray. It was a message from the universe, a demonstration that nature can accelerate individual particles to energies that seem to belong to a completely different scale of reality. But the "Oh my God" particle, as extraordinary as it was, sits at the very top of a much broader spectrum. Cosmic rays arrive at Earth with a huge range of energies. The vast majority of cosmic rays are relatively modest. They carry energies of a few 100 million electron volts to a few billion electron volts. An electron volt is a tiny unit of energy, the energy gained by a single electron when it is accelerated through a potential difference of 1 volt. A few billion electron volts sounds like a lot, but in everyday terms, it is minuscule. A mosquito in flight carries roughly 10,000 times more kinetic energy than one of these ordinary cosmic rays. These low-energy cosmic rays are extremely common. Thousands of them pass through your body every single minute of every day. Right now, as you are listening to this, cosmic rays are streaming through you. Through your skin, through your bones, through your brain. You cannot feel them because each one carries so little energy that its interaction with your body is negligible. A single cosmic ray might knock an electron off an atom in one of your cells. It might cause a tiny bit of ionization in your tissues. But your body is made of trillions upon trillions of atoms. Losing one electron from one atom is like removing one grain of sand from a beach. It makes no meaningful difference. Moving up the energy scale, we find cosmic rays in the range of trillions of electron volts, or tera-electron volts. These are less common than the lower energy variety, but still abundant. You might detect roughly 1 per square meter per second. They carry more energy per particle Enough to be scientifically interesting, but still far below anything you would notice in everyday life. Further up, still are the cosmic rays in the peta-electron volt range. That is 1,000,000 billion electron volts. These are rare, arriving at a rate of about 1 per square meter per year. They carry significant energy for a subatomic particle, but still nothing compared to everyday objects. Then, at the extreme end, we reach the ultra-high energy cosmic rays. These are the cosmic rays above 1 billion electron volts, or 1 exa-electron volt. These are extraordinarily rare. You might detect 1 per square kilometer per year. Some detectors wait months or even years between events at these energies. And at the very top, above 10 billion electron volts, we find particles like the oh my god particle. These arrive at a rate of perhaps 1 per square kilometer per century. They are among the rarest phenomena in all of physics. The reason this energy spectrum matters is that it tells us something fundamental about the universe. Low energy cosmic rays are common because they are relatively easy to produce. A modest stellar explosion, a mildly active region of a galaxy, even the sun itself can produce low energy cosmic rays. Our sun regularly emits protons and heavier nuclei during solar flares and coronal mass ejections. These solar energetic particles are technically cosmic rays, though they are at the very bottom of the energy ladder. But the higher you go in energy, the harder it becomes to accelerate particles. You need stronger magnetic fields, you need larger acceleration regions, you need more violent events. Each step up the energy ladder requires a more extreme astrophysical environment. This is why ultra-high energy cosmic rays are so rare. Whatever is producing them, whatever cosmic mechanism is accelerating single protons to the energy of a thrown baseball, it must be something extraordinarily violent. Something operating at scales and intensities that push the boundaries of what physics allows. And that is a clue about the most extreme environments in the universe. Let's go back to that contrast for a moment, because I want to make sure it truly lands. A proton has a mass of about 1.67 times 10 to the negative 27 kilograms. You could line up a billion protons, and they would not weigh as much as a grain of salt. A single proton is, for all practical purposes, nothing. It is so small and so light that it exists in a realm completely divorced from everyday experience. You will never hold a proton in your hand. You will never feel one hit your skin. You will never see one with any instrument that works on human scales. And yet, when one of these almost non-existent particles is accelerated close enough to the speed of light, it carries the energy of a baseball. Think about what that means. Something that weighs essentially nothing, carrying the same punch as something you can hold in your hand and throw. This is not an analogy. This is not an approximation. This is a literal, measured fact. The oh my god particle, a single proton, had the same kinetic energy as a baseball pitched across a diamond. That single proton could have heated a teaspoon of water by over 2 degrees Celsius. That single proton, if it hit a small object, could have physically moved it. A proton. Moving an object you can see, that is what speed does when it approaches the speed of light. It transforms the negligible into the devastating. It takes something that should not matter, that should pass through the world without leaving a trace, and turns it into something that hits with the force of the everyday world. This is perhaps the most important thing to understand about cosmic rays. They are not exotic forms of energy. They are not mysterious radiation from some unknown source. They are ordinary matter, Protons. The same protons that exist inside every atom of hydrogen, inside every molecule of water, inside every star in the universe. There is nothing special about a cosmic ray proton in terms of what it is made of. It is the same particle you would find inside your own body. What makes it extraordinary is purely and entirely how fast it is going. Speed is the only thing that separates a harmless proton in your drinking water from a cosmic ray that carries the energy of a fastball. The particle itself is identical. The physics that governs it is identical. The only difference is velocity, and that difference changes everything. It is worth noting that cosmic rays are not a rare or exotic phenomenon. They are everywhere. The Milky Way is saturated with them, a constant background of high-energy particles streaming through the space between stars in every direction. The total energy density of cosmic rays in the Milky Way is roughly comparable to the energy density of starlight, of the galaxy's magnetic field, and of the interstellar gas. They are not a minor footnote in astrophysics. They are a major player. They affect the chemistry of interstellar gas. They influence how clouds of gas collapse to form new stars. They contribute to the ionization of molecular clouds, which in turn affects how those clouds behave. Cosmic rays even play a role in the large-scale dynamics of the galaxy itself, exerting pressure on the interstellar medium and helping to drive galactic winds, streams of gas that flow out of the galaxy's disk. You could remove all the visible light from the Milky Way and cosmic rays would still be there, still carrying roughly the same amount of energy, still streaming through the galaxy in every direction. They are an invisible, but enormously important component of the universe we live in. And here is something else most people do not realize. Cosmic rays are not a recent discovery. They have been bombarding Earth for as long as Earth has existed. For 4.5 billion years, cosmic rays have been raining down on our planet. They have been striking our atmosphere, producing cascades of secondary particles, depositing energy into the air and the ground and the oceans. They have been hitting living cells since the very first life forms appeared. In fact, cosmic rays may have played a role in the origin and evolution of life itself. Every so often, a cosmic ray or one of its secondary particles strikes a molecule of DNA in a living cell. Most of the time, the cell repairs the damage. Sometimes, the cell dies, and very rarely, the damage changes the DNA in a way that is not lethal, but is heritable. A mutation. Most mutations are harmful or neutral, but occasionally, very rarely, a mutation is beneficial. It gives the organism an advantage. Over billions of years, these random cosmic ray-induced mutations, along with mutations from other sources, have contributed to the slow, grinding process of evolution. You are, in some small but real sense, a product of cosmic rays. Some of the genetic variations that make you who you are, that distinguish you from every other human being, might trace their origins back to a single cosmic ray particle that struck one of your ancestors' cells millions of years ago. The violence of the cosmos is written into your DNA. So when we talk about cosmic rays, we are not talking about something remote or abstract. We are talking about a phenomenon that is intimately connected to our existence, to the chemistry of our galaxy, to the evolution of life on our planet, and to the most extreme physical processes the universe is capable of producing. We are talking about ordinary particles driven to extraordinary speeds by the most violent events in the cosmos. Particles that have been traveling for millions of years across the emptiness between stars. carrying the fingerprint of whatever cataclysmic event launched them. Particles so energetic that a single one can carry the punch of a thrown ball, even though it weighs essentially nothing. That is what a cosmic ray really is. Not a ray, not a beam of light, a bullet. A subatomic bullet fired by the universe itself. And the question you should be asking now is the same question that kept physicists awake at night for decades after they first discovered these particles. What in the universe could possibly accelerate something so small to something so fast? What kind of event? What kind of environment? What kind of cosmic machinery could take an ordinary proton and give it the kinetic energy of a macroscopic object? That question leads us to some of the most violent and extreme places the universe has to offer. So something out there is accelerating ordinary protons to nearly the speed of light. Something is taking particles that weigh almost nothing and pumping them so full of kinetic energy that a single one can rival a thrown baseball. The question is, what? What kind of cosmic machinery could do this? And the answer takes us to some of the most violent, extreme, and terrifying environments the universe has ever produced. Let's start with the most common source, the one responsible for the vast majority of cosmic rays that pass through our galaxy: supernova remnants. When a massive star dies, it does not fade away quietly. A star that is more than about 8 times the mass of our Sun will end its life in a catastrophic explosion called a supernova. In the final moments of its existence, the star's core collapses under its own gravity. The outer layers, no longer supported, come crashing inward. They slam into the collapsing core and bounce. The rebound sends a shockwave tearing outward through the star at speeds of 10,000 to 30,000 kilometers per second. That shockwave rips the star apart. In a matter of seconds, the star goes from a relatively stable object to an expanding cloud of superheated debris blasting outward into space. For a few weeks, the explosion can outshine an entire galaxy. A single dying star, for a brief moment, produces more light than hundreds of billions of stars combined. But the explosion itself is not what accelerates cosmic rays. What matters is what happens afterward. After the initial blast, the debris keeps expanding outward into the space surrounding the dead star. This expanding shell of gas, called a supernova remnant, plows into the interstellar medium, the thin gas and dust that fills the space between stars. And where this expanding shell meets the surrounding gas, a shockwave forms. Not the original shockwave from the explosion, but a persistent, long-lived shockwave at the boundary between the fast-moving debris and the slower surrounding material. This shockwave can persist for tens of thousands of years, and it is this shockwave, this boundary between fast and slow, between chaos and calm, that acts as a cosmic particle accelerator. The mechanism is called diffusive shock acceleration, and it is one of the most elegant processes in astrophysics. Here is how it works. Imagine you are a proton drifting through interstellar space at a modest speed. Then, the expanding shockwave from a supernova remnant sweeps past you. You get caught up in it. The shock front is a region of compressed, turbulent gas threaded with tangled magnetic fields. And those magnetic fields are the key. Charged particles, like protons, cannot move in straight lines through magnetic fields. The magnetic field grabs them and forces them to spiral along the field lines, curving their path, changing their direction. In the turbulent region around a supernova shockwave, the magnetic fields are chaotic. They point in every direction. They tangle and twist and fold over themselves. A proton entering this region gets bounced around like a ball in a pinball machine. The magnetic fields act as bumpers, deflecting the proton this way and that, sending it careening through the turbulent gas. Now here is the crucial part. The shockwave has two sides. On one side, you have the fast-moving debris from the supernova, plowing outward at thousands of kilometers per second. On the other side, you have the relatively stationary interstellar gas that has not yet been hit by the shock. The proton bounces back and forth across this boundary. It crosses from the fast side to the slow side, gets deflected by magnetic fields, and crosses back again. Each time it crosses the shock front, it picks up a little bit of energy. Not a lot, just a small boost. Maybe a fraction of a percent increase in speed each time. But here is what makes this process so powerful. The proton does not cross once and leave. It crosses again and again and again, hundreds of times, thousands of times, potentially millions of times. Each crossing adds a little more energy, a little more speed. The energy gains compound, like interest in a bank account. After enough crossings, the proton has been accelerated to extraordinary speeds. Think of it like a tennis ball bouncing between two walls that are moving toward each other. Each time the ball bounces off one wall and hits the other, it picks up a little speed from the moving wall. After many bounces, the ball is moving much faster than either wall. The supernova shockwave works the same way. The proton bounces back and forth across the shock front, gaining energy with each crossing, until it reaches speeds close to the speed of light. Eventually, the proton gains so much energy that the magnetic fields can no longer contain it. It escapes the supernova remnant entirely, flying off into interstellar space as a newly minted cosmic ray. This entire process takes time. A proton might spend thousands of years bouncing back and forth in the shock region before it reaches its maximum energy and escapes. But supernova remnants last for tens of thousands of years before they fade, so there is plenty of time for acceleration, and the process is happening to countless protons simultaneously. A single supernova remnant can accelerate billions upon billions of protons over its lifetime. This mechanism was first proposed in the late 1940s by the physicist Enrico Fermi, which is why it is sometimes called Fermi acceleration. Fermi's core insight was that charged particles bouncing off moving magnetic structures gain energy over time. The specific version involving shock waves, called first-order Fermi acceleration, was refined in the late 1970s by several groups independently. It remains one of the most successful theories in astrophysics. It explains not just the existence of cosmic rays, but their energy spectrum, the specific way their numbers decrease as you go to higher energies. The theory predicts a power law distribution, where the number of cosmic rays at a given energy drops off as the specific power of that energy. And that is exactly what we observe. The match between theory and observation is remarkably good, at least up to a point. We do not have to take this theory on faith. We have direct observational evidence that supernova remnants are accelerating particles to extreme energies. And some of the best evidence comes from one of the most famous objects in the night sky, the Crab Nebula. In the year 1054, Chinese astronomers recorded the sudden appearance of a new star in the constellation we now call Taurus. It was so bright that it was visible during the day for 23 consecutive days. It remained visible to the naked eye at night for nearly 2 years before fading from view. What those astronomers witnessed was a supernova, the explosive death of a massive star roughly 6,500 light years from Earth. Today, nearly 1,000 years later, the debris from that explosion is still expanding outward. We call it the Crab Nebula, and it is one of the most studied objects in all of astronomy. At the center of the Crab Nebula sits a pulsar, a rapidly spinning neutron star that rotates about 30 times per second. This pulsar is the compressed core of the star that exploded, and it powers the nebula with a constant wind of energetic particles and magnetic fields. The expanding shell of gas from the original explosion, threaded with intense magnetic fields, is exactly the kind of environment where diffusive shock acceleration should be operating. And we can see the evidence directly. When charged particles spiral through magnetic fields, they emit a specific type of radiation called synchrotron radiation. This radiation has a distinctive signature. It is polarized, meaning the light waves oscillate in a preferred direction, and it spans a broad range of frequencies from radio waves through visible light and into X-rays. When astronomers point their telescopes at the Crab Nebula and analyze the light, they find exactly this signature. The nebula is glowing with synchrotron radiation, proof that electrons are being accelerated to relativistic speeds within its magnetic fields. If electrons are being accelerated, protons and heavier nuclei are almost certainly being accelerated as well, because the same shock waves and magnetic fields that grab electrons will also grab any charged particle. But the most compelling evidence came from gamma-ray observations. In 2004 and the years that followed, gamma-ray telescopes, including the HESS array in Namibia, the MAGIC telescopes in the Canary Islands, and the Veritas array in Arizona, detected very high-energy gamma rays coming from several supernova remnants. One of the most important was a remnant called RxJ 1713.7-3946, the remains of a star that exploded roughly 1,600 years ago. The gamma rays detected from this remnant had energies exceeding 1 trillion electron volts. These gamma rays are produced when accelerated protons collide with gas in and around the remnant, producing neutral pions that decay into gamma-ray photons. The spatial pattern of the gamma-ray emission matched the shockwave structure of the remnant almost perfectly. The gamma rays were brightest exactly where the shockwave was strongest. This was essentially a photograph of cosmic ray acceleration in action. We could see where it was happening, map its structure, and measure the energies involved. Another landmark came from the LHASO Observatory in China, which in 2021 detected gamma rays from multiple sources within the Milky Way at energies exceeding 1 peta-electron volt, 1,000 trillion electron volts. These gamma rays almost certainly originate from interactions involving cosmic ray protons at even higher energies, providing the strongest evidence yet that sources within our galaxy can accelerate particles to the peta-electron volt range and possibly beyond. These observations transformed cosmic ray physics from a largely theoretical field into an observational one. We are no longer just theorizing about where cosmic rays come from. We are watching the acceleration happen in real time, seeing the shock waves glow with the radiation produced by particles being boosted to incredible energies. The universe has provided us with natural laboratories, and we are finally able to read the data. Another supernova remnant worth mentioning is N1006, the remains of a supernova that was observed in the year 1006. At its peak, SN 1006 was the brightest stellar event ever recorded in human history. It was bright enough to cast shadows at night. Egyptian and European observers noted it. Chinese and Japanese astronomers documented it in detail. Today, 1,000 years later, the expanding shell of debris is still visible as a faint ring of gas about 60 light-years across. X-ray observations from the Chandra Space Telescope reveal that the edges of this ring, the shock fronts where the expanding debris meets the surrounding gas, are producing intense synchrotron radiation. Electrons at these shock fronts are being accelerated to energies of at least 100 trillion electron volts. This is direct, visible proof that the shock acceleration mechanism works. That supernova remnants are indeed the cosmic particle accelerators that theory predicted. Supernova remnants are efficient cosmic ray factories. Astronomers estimate that about 10% of the total energy released in a supernova explosion, which is an enormous amount of energy, gets channeled into accelerating cosmic rays. That is roughly 10 to the 43 joules of energy per supernova converted into fast-moving particles. And supernovae happen regularly. In a galaxy like the Milky Way, a star explodes roughly once or twice per century. That means over the lifetime of the galaxy, trillions of supernovae have occurred, each one pumping out cosmic rays. The cumulative result is the sea of cosmic rays that fills the galaxy today. But there is a limit. Supernova remnants cannot accelerate particles to arbitrarily high energies. The maximum energy depends on the size of the acceleration region and the strength of the magnetic fields. For typical supernova remnants, the maximum energy is somewhere around a few times 10 to the 15 electron volts. That is a few peta-electron volts. Impressive by everyday standards, but far below the energies of the most extreme cosmic rays ever detected. The oh my god particle had an energy of about 3 times 10 to the 20 electron volts. That is 100,000 times higher than what supernova remnants can produce. Something else must be responsible for the most energetic cosmic rays. Something far more powerful than an exploding star. This brings us to one of the most dramatic environments in the universe, the regions around supermassive black holes. At the center of most large galaxies, including our own Milky Way, there sits a black hole with a mass millions or even billions of times greater than the Sun. In some galaxies, these black holes are actively feeding. Gas, dust, and even stars fall toward the black hole, spiraling inward in a swirling disk called an accretion disk. As material falls inward, it heats up to extraordinary temperatures, glowing with intense radiation across the electromagnetic spectrum. These feeding black holes power what astronomers call active galactic nuclei. And some of them produce something even more spectacular. Jets. Enormous beams of matter and energy that shoot outward from the poles of the accretion disk at speeds approaching the speed of light. These jets can extend for millions of light years, punching through the surrounding galaxy and reaching far into intergalactic space. They are among the most powerful, sustained phenomena in the universe. The jets from active galactic nuclei are ideal environments for particle acceleration. They contain intense magnetic fields, moving at relativistic speeds, threading through hot plasma. Charged particles caught in these jets experience conditions far more extreme than anything found in a supernova remnant. The magnetic fields are stronger, The velocities are higher. The acceleration region is vastly larger. A supernova remnant might be a few dozen light-years across. A jet from an active galactic nucleus can extend for millions of light-years. This means particles can be accelerated over much larger distances and for much longer times, reaching much higher energies. Many astrophysicists believe that the jets of active galactic nuclei are responsible for at least some of the ultra-high energy cosmic rays, the particles above 10 to the 18 electron volts. These jets have the raw power, the magnetic field strength, and the sheer size needed to accelerate protons to the staggering energies we observe. The physics is similar to what happens in supernova remnants. Shock waves form within the jets, and particles bounce back and forth across these shocks, gaining energy with each crossing. But the scale is incomparably larger. Consider a galaxy like M87, which sits about 54 million light-years from Earth in the Virgo cluster. M87 has a supermassive black hole at its center, with a mass of about 6.5 billion times the mass of the Sun. This black hole powers an enormous jet that extends for at least 5,000 light-years. The jet is visible in optical, radio, and X-ray light. It is a river of relativistic plasma, matter moving at close to the speed of light, carrying magnetic fields and accelerating particles as it goes. An environment like this could plausibly accelerate protons to energies of 10 to the 20 electron volts or even higher. The energy available is almost limitless. The accretion disk around a supermassive black hole can release more energy than an entire galaxy of stars. Channeling even a tiny fraction of that energy into particle acceleration could produce the most energetic cosmic rays we have ever detected. To appreciate just how extreme these environments are, consider what is actually happening in the accretion disk around a supermassive black hole. Gas and dust fall toward the black hole, but they do not fall straight in. Angular momentum forces the material into a swirling disk, spiraling inward like water going down a drain, but on a vastly larger scale. As the material spirals closer to the black hole, it gets compressed. Friction between layers of gas moving at different speeds heats the material to extraordinary temperatures. The inner regions of the accretion disk can reach temperatures of millions of degrees, and the superheated corona above the disk can reach hundreds of millions of degrees. At these temperatures, the gas is not just hot. It is a plasma, a soup of free electrons and ions moving at significant fractions of the speed of light. The gravitational energy being released as matter falls inward is staggering. For every kilogram of matter that spirals into the accretion disk, the process releases roughly 10% of that mass's energy equivalent, as described by Einstein's famous equation. That is roughly 15 times more efficient than nuclear fusion, the process that powers stars. A supermassive black hole actively consuming matter is one of the most efficient energy-releasing mechanisms in the known universe, and some of that energy gets channeled into the jets. The exact mechanism that forms jets is still debated, but it likely involves the twisting of magnetic field lines by the spinning black hole and the rotating accretion disk. The magnetic fields wind up like a spring and eventually snap outward along the rotational axis, launching columns of magnetized plasma at nearly the speed of light. These jets carry enormous power. The jet from M87, for example, is estimated to carry a total power of roughly 10 to the 37 watts. That is tens of billions of times the total power output of our sun, sustained continuously for millions of years. A particle caught in this environment, bouncing between shocks within the jet, buffeted by magnetic fields carrying more energy than entire galaxies of stars, can be accelerated to almost any energy imaginable. But active galactic nuclei are not the only candidate for producing ultra-high energy cosmic rays. There are other extreme environments that could contribute. Rapidly spinning neutron stars, the dense remnants left behind when certain massive stars explode, are another possibility. A neutron star is an object about 12 miles across, but containing 1.5 to 2 times the mass of our Sun. The density is almost beyond comprehension. A teaspoon of neutron star material would weigh about 4 billion tons on Earth. Some neutron stars spin incredibly rapidly, rotating hundreds of times per second. These rapidly spinning neutron stars generate powerful magnetic fields, among the strongest in the universe. A special class of neutron stars called magnetars has magnetic fields that are 1,000 trillion times stronger than Earth's magnetic field. The region around a rapidly spinning, highly magnetized neutron star is an intense environment where electric fields can accelerate charged particles to very high energies. The magnetosphere of such a star, the region dominated by its magnetic field, acts like a natural particle accelerator. Protons and heavier nuclei caught in this magnetosphere can be whipped up to relativistic speeds and flung outward into space. The maximum energy achievable in neutron star magnetospheres is debated. Some models suggest that the most extreme magnetars could accelerate particles to energies approaching 10 to the 18 or even 10 to the 19 electron volts. That is extremely high, though still below the oh my god particles energy. Nevertheless, neutron stars are thought to contribute significantly to the cosmic ray population at intermediate energies, filling the gap between what supernova remnants can produce and what active galactic nuclei handle at the very top. There is another candidate source that deserves mention, one that involves the most energetic events in the universe since the Big Bang itself: gamma-ray bursts. These are brief, extraordinarily intense flashes of gamma-ray radiation that occur at random positions in the sky. They last anywhere from a fraction of a second to several minutes. During that brief window, a single gamma-ray burst can release more energy than the Sun will produce in its entire 10 billion year lifetime. There are two main types: short gamma-ray bursts, lasting less than about 2 seconds, are thought to be caused by the collision and merger of two neutron stars. Long gamma-ray bursts, lasting more than 2 seconds, are thought to result from the collapse of an extremely massive star. A star so large that when it dies, it does not just explode. Its core collapses directly into a black hole, and the infalling material produces jets that punch through the collapsing star and erupt into space. The jets produced during gamma-ray bursts are among the most extreme environments known to physics. They move at speeds exceeding 99% of light speed. They carry intense magnetic fields. And the shocks that form within and around these jets could potentially accelerate particles to the very highest energies ever observed. Some physicists have proposed that gamma-ray bursts are responsible for the most extreme ultra-high energy cosmic rays, including particles at the level of the oh my god particle. The energetics are certainly right. A single gamma-ray burst releases enough energy to potentially accelerate enormous numbers of particles to ultra-high energies. The problem is proving it. Gamma-ray bursts are transient events. They happen briefly and then fade. Cosmic rays do not travel in straight lines. because magnetic fields in intergalactic space deflect them. So we cannot simply trace a cosmic ray back to its source the way we can trace a beam of light. The cosmic ray might have been deflected many times during its journey, arriving at Earth from a completely different direction than where it was originally launched. This makes it extremely difficult to associate any particular cosmic ray with any particular source. This difficulty of tracing cosmic rays back to their origins is one of the central challenges in cosmic ray physics. Photons, particles of light, travel in straight lines through empty space. If you detect a photon coming from a specific direction, you know the source is in that direction. Cosmic rays do not have this luxury. They are electrically charged. Every time they encounter a magnetic field, and the universe is filled with magnetic fields, their path bends. Over millions of light years of travel, a cosmic ray's path can be bent and twisted so many times that its arrival direction bears little resemblance to the direction of its source. This is especially true for lower energy cosmic rays, which are more easily deflected. For ultra-high energy cosmic rays, the deflections are smaller because the particles are so energetic that magnetic fields have less effect on them. This is one reason physicists are so interested in ultra-high energy cosmic rays. They are the ones most likely to point roughly back toward their sources. Now, there is a fascinating constraint on where the most energetic cosmic rays can come from. It is called the GZK limit, named after physicists Kenneth Grayson, Georgy Zatsepin, and Vadim Kuzmin, who predicted it in 1966. The idea is elegant and sobering. The universe is filled with a faint glow of microwave radiation left over from the Big Bang. This is the cosmic microwave background, a sea of low-energy photons that permeates all of space. These photons are everywhere. Every cubic centimeter of space contains about 400 of them on average. They are incredibly low energy, corresponding to a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. For most particles, these photons are utterly irrelevant. A proton moving at ordinary speeds would not even notice them. But for a proton moving at ultra-high energies, these faint microwave photons become a problem. When an ultra-high energy proton collides with a cosmic microwave background photon, the collision can produce new particles, specifically pions. This process is called photopion production. The proton loses a significant fraction of its energy in each collision. And because the cosmic microwave background photons are everywhere, the proton encounters them constantly. Over long distances, these interactions drain the proton's energy. The result is that a proton above a certain energy threshold, about 5 × 10⁻19 electron volts, cannot travel more than a few 100 million light years through the universe, without losing so much energy that it drops below the threshold. This means that any ultra-high energy cosmic ray detected on Earth with an energy above the GZK threshold must have originated relatively nearby, in cosmic terms, within a few 100 million light years. Beyond that distance, the cosmic microwave background would have sapped its energy during the journey. This is an incredibly useful constraint. It tells us that the sources of the most energetic cosmic rays must be in our cosmic neighborhood. Not in our galaxy necessarily, but within a few 100 million light years. That narrows the search. There are only so many active galactic nuclei, so many powerful radio galaxies, so many candidate sources within that radius. And yet, despite decades of searching, we have not been able to conclusively identify the specific sources of the most energetic cosmic rays. The arrival directions of these particles show some hints of clustering, some suggestions that they might be coming from particular regions of the sky. But the evidence is not definitive. The deflections caused by magnetic fields, even the relatively small deflections experienced by ultra-high energy cosmic rays, smear out the arrival directions enough that pinpointing exact sources remains elusive. What the energy spectrum of cosmic rays does tell us clearly is that there must be multiple classes of accelerators. The spectrum is not smooth. It has features, subtle changes in slope that indicate transitions between different source populations. At energies below about 3 × 10⁻15 electron volts, the spectrum follows one power law slope. This region is believed to be dominated by cosmic rays from within the Milky Way, primarily accelerated by supernova remnants. At this energy, there is a slight steepening of the spectrum, a feature astronomers call the knee. The knee is thought to mark the maximum energy achievable by typical supernova remnants. Above the knee, the spectrum steepens slightly, indicating that fewer particles are being produced at these energies. Supernova remnants are running out of accelerating power. Then, at about 3 × 10⁻18 electron volts, the spectrum flattens again. This feature is called the ankle. The ankle is believed to mark the transition from galactic cosmic rays to extragalactic cosmic rays. Above this energy, the particles are thought to come from sources outside the Milky Way, from active galactic nuclei, gamma-ray bursts, or other powerful extragalactic accelerators. The change in spectrum slope at the ankle tells us that a new population of sources is taking over. Sources that can accelerate particles to much higher energies than anything within our galaxy. There is a beautiful logic to this picture. The universe operates a hierarchy of particle accelerators. At the bottom, modest sources like the Sun produce low-energy particles. In the middle, supernova remnants within our galaxy produce cosmic rays up to peta-electron volt energies. And at the top, the most extreme extragalactic sources, the jets of supermassive black holes, the magnetospheres of exotic neutron stars, the fireballs of gamma-ray bursts produce the rare but spectacularly energetic particles that arrive at the very highest energies. Each class of accelerator has its own maximum energy, determined by the size of the acceleration region, the strength of the magnetic fields, and the velocity of the shocks. Small accelerators produce low-energy particles. Large accelerators produce high-energy particles. And the most extreme accelerators in the universe produce particles with energies that seem almost absurd. The universe, it turns out, is not just passively sitting there. It is actively and continuously accelerating particles to incredible energies using magnetic fields and shock waves on scales ranging from the relatively modest, a supernova remnant a few light years across, to the almost incomprehensibly vast, a jet from a supermassive black hole stretching for millions of light years. The entire cosmos is threaded with these acceleration regions, each one pumping out charged particles, filling the galaxy and the universe with a steady rain of high-energy matter. And those particles, once launched, travel for millions of years across the void. They cross the emptiness between stars. They thread through the magnetic fields of the galaxy. Some of them escape the Milky Way entirely, while others arrive from far beyond it, crossing millions of light years of intergalactic space, dodging the energy-sapping photons of the cosmic microwave background. slowly losing direction as magnetic fields nudge their paths, until finally, after a journey that might have begun before multicellular life even existed on Earth, they arrive here. They slam into our atmosphere. And what happens next is a story of its own. We have talked about what cosmic rays are. We have talked about where they come from. But we have not yet fully reckoned with the thing that makes them truly extraordinary. Their energy, their sheer, almost absurd kinetic energy. Because the fact that a single proton can carry the energy of a thrown baseball is not just a fun piece of trivia. It is a window into how the universe behaves at its most extreme. And understanding why this happens, understanding the physics that allows something so small to hit so hard, requires us to confront one of the deepest and strangest truths about the way nature works. Let's start from the beginning. From the most basic physics you probably learned in school, kinetic energy. The energy an object has because it is moving. In everyday life, this is simple. If you throw a ball, it has kinetic energy. If you drive a car, it has kinetic energy. The faster something moves and the heavier it is, the more kinetic energy it carries. The formula is straightforward. Kinetic energy equals 1/2 times the mass of the object times the square of its velocity. This formula works beautifully for everything in your daily life. Anything moving at speeds that are small compared to the speed of light, which is everything you have ever directly experienced, because the fastest things in everyday human life are still moving at a tiny, tiny fraction of light speed. A bullet travels at maybe 1 kilometer per second. The fastest manned vehicle ever, the Apollo 10 command module, reached about 11 kilometers per second. These are impressive speeds by human standards. But the speed of light is about 300,000 kilometers per second. Even the Apollo spacecraft was traveling at only about 0.004% of light speed. At these modest velocities, the classical formula works perfectly, and it tells you something intuitive. If you double the speed of an object, you quadruple its kinetic energy. If you triple the speed, you get 9 times the energy. The energy increases as the square of the velocity. This means speed matters more than mass when it comes to kinetic energy. A small object moving very fast can carry more energy than a large object moving slowly. A bullet weighs only a few grams, far less than a thrown rock. But because it moves so much faster, it carries more kinetic energy. A small meteor entering Earth's atmosphere can carry more energy than a nuclear weapon, because it is moving at tens of kilometers per second. Speed amplifies energy, and at everyday speeds, this amplification follows a clean, predictable pattern. Double the speed, quadruple the energy. Triple the speed, 9 times the energy. 10 times the speed, 100 times the energy. But this pattern does not hold forever. As an object approaches the speed of light, something fundamental changes. The classical formula breaks down. It stops being accurate. It stops describing reality. And what replaces it is far stranger and far more dramatic. In 1905, Albert Einstein published his theory of special relativity. Among its many revolutionary consequences was a complete overhaul of how we understand motion, energy, and mass at high speeds. Einstein showed that the classical formula for kinetic energy is only an approximation that works at low speeds. At speeds approaching the speed of light, a different set of equations takes over. And these equations describe a universe that behaves very differently from what our everyday intuition would suggest. The key concept is something called the Lorentz factor, named after the Dutch physicist Hendrik Lorentz. The Lorentz factor is a number that depends on how fast an object is moving relative to the speed of light. At low speeds, the Lorentz factor is very close to 1. At half the speed of light, it is about 1.15. At 90% of light speed, it is about 2.3. At 99% of light speed, it is about 7.1. At 99.9%, it is about 22.4. And as you keep adding nines after the decimal point, the Lorentz factor climbs faster and faster. At 99.9999% of light speed, it is about 707. At 99.999999%, it climbs to about 7,000. Add a few more nines, and it reaches into the hundreds of thousands. The Lorentz factor describes how much the properties of a moving object differ from what you would expect, based on everyday physics. Time dilation, length contraction, the increase in effective inertia, all of these effects are governed by the Lorentz factor. And most importantly for our discussion, the total energy of a moving particle is equal to its rest energy, the energy locked up in its mass, multiplied by the Lorentz factor. This means that as a particle approaches light speed, its energy does not just increase, it explodes. It does not follow the gentle square of the velocity pattern from classical physics. Instead, it climbs on a curve that goes nearly vertical as you approach light speed. The closer you get, the steeper the climb. Adding that last fraction of a percent of speed, going from 99.999% to 99.9999%, increases the energy by a far greater factor than going from 0 to 90%. The universe, in a sense, fights you harder and harder the closer you get to the ultimate speed limit. Each tiny increment of additional speed requires a disproportionately enormous increase in energy. This is not a gradual scaling. It is an exponential explosion that approaches infinity as you approach the speed of light. Let me make this concrete. A proton at rest has a rest energy of about 938 million electron volts. That is the energy equivalent of its mass. Given by Einstein's famous equation, energy equals mass times the speed of light squared. This is a fixed number. Every proton has this same rest energy. Now let's accelerate this proton to different speeds and see what happens to its total energy. At 10% of light speed, the proton's total energy is about 943 million electron volts, barely more than its rest energy. The kinetic energy it has gained is only about 5 million electron volts. At 50% of light speed, the total energy rises to about 1,083 million electron volts. The kinetic energy is now about 145 million electron volts, still relatively modest. At 90% of light speed, the total energy jumps to about 2,150 million electron volts. The kinetic energy has now surpassed the rest energy itself. The particle carries more energy from its motion than the energy locked in its own mass. Now, things start to get interesting. At 99% of light speed, the total energy is about 6,600,000,000 electron volts. The kinetic energy is now about 6 times the rest energy. At 99.9%, the total energy rises to about 21 billion electron volts. At 99.99%, it is about 66 billion electron volts. And at the speed of the oh my god particle, which was traveling at 99.9999999% of the speed of light, the total energy was about 3 times 10 to the 20 electron volts. That is roughly 320 billion electron volts. The Lorentz factor for this particle was about 340 billion. Its kinetic energy was 340 billion times greater than its rest energy. The energy of motion, the energy gained purely from speed, utterly dwarfed the energy contained in the particle's own mass. Let me translate those numbers out of particle physics units and into something tangible, because this is where it gets truly astonishing. The oh my god particle carried about 50 joules of kinetic energy. 50 joules is the energy of a baseball thrown at about 60 miles per hour. It is approximately the energy of a tennis ball served at about 95 miles per hour. It is the amount of energy you would feel if someone dropped a brick on your foot from about waist height. These are everyday energies. Energies you can feel. Energies that can bruise skin, break glass, knock things off a table. And they were concentrated into a single proton. Think about what that means in terms of energy density. A baseball has a mass of about 145 grams. A proton has a mass of about 1.67 times 10 to the negative 24 grams. The proton is lighter than the baseball by a factor of roughly 10 to the 26. That is 100 trillion times lighter. And yet they are carrying the same kinetic energy. The energy in the proton is concentrated into a space unimaginably smaller than the baseball. The energy density, the amount of energy per unit of mass or per unit of volume, is beyond anything that exists in everyday experience. Nothing in your daily life even remotely approaches this kind of energy concentration. A bullet is energetic. A bolt of lightning is energetic. An explosion is energetic. But none of them concentrate their energy into a single subatomic particle. The oh my god particle was carrying macroscopic energy in a microscopic package. That combination is what makes ultra high energy cosmic rays so remarkable and so destructive when they interact with matter. To build more intuition for how extreme this energy is, let's do some comparisons. Consider a grain of sand. A small grain of sand weighs about 1 milligram, roughly 10 to the negative 6 kilograms. If you dropped a grain of sand from a height of about 4 meters, about the height of a single-story building, it would hit the ground with a kinetic energy of about 0.00004 joules. The oh my god particle carried about 1 million times more kinetic energy than a grain of sand dropped from a building. And the proton weighs trillions of times less than the grain of sand. Now consider a bowling ball. A typical bowling ball weighs about 6 kilograms. If you dropped a bowling ball from a height of about 85 centimeters, roughly waist height on a small child, it would hit the ground with about 50 joules of kinetic energy. The same energy as the oh my god particle. That is the comparison. A subatomic particle carrying the same energy as a bowling ball dropped from knee height. These comparisons are not exaggerations. They are not metaphors. They are straightforward applications of the physics of kinetic energy. The numbers are real. A single proton, traveling close enough to the speed of light, carries the same punch as a falling bowling ball or a thrown baseball. Now, let's push this further and think about what happens if this energy is actually delivered to a target. Because energy by itself is just a number. What matters is what happens when that energy interacts with matter. And this is where cosmic rays become fundamentally different from other forms of radiation. Consider a gamma ray photon from space. Gamma rays also carry energy, sometimes a lot of it. The most energetic gamma rays ever detected from astrophysical sources reach about 1 peta-electron volt. 1,000 trillion electron volts. That sounds impressive until you compare it to an ultra-high energy cosmic ray. The oh my god particle carried roughly 300,000 times more energy than even the most energetic gamma ray ever observed from an astrophysical source, and the nature of the energy delivery is completely different. A gamma ray deposits its energy through electromagnetic interactions, absorbed by atoms or converted into particle-antiparticle pairs. These are relatively gentle processes at the atomic level, but a cosmic ray proton does not interact gently. It carries its energy as sheer kinetic motion of a massive charged particle, and when it strikes an atomic nucleus, the collision is governed by the strong nuclear force, the most powerful force in nature, the force that holds atomic nuclei together. The result is not absorption. It is a direct nuclear impact. The cosmic ray proton smashes into the target nucleus with such force that it can shatter the nucleus entirely, breaking it apart into its constituent protons and neutrons and scattering them in every direction. But that is only the beginning. Because when a cosmic ray carries enough energy, the collision does not just break things apart, it creates new things. This is one of the most profound consequences of Einstein's mass-energy equivalence. Energy and mass are interchangeable. Given enough energy, you can create entirely new particles from pure kinetic energy. The collision between a cosmic ray proton and an atmospheric nucleus is energetic enough to create dozens, hundreds, or even thousands of new particles that did not exist before the collision. Pions, kaons, etemesons, protons, antiprotons, neutrons, antineutrons, hyperons, and exotic particles that do not exist in ordinary matter. All of these spring into existence from the energy of the impact, manufactured on the spot by the conversion of kinetic energy into mass. This is not a theoretical possibility. It has been observed directly. In fact, before particle accelerators were invented, cosmic rays were the only source of high-energy particle collisions available to physicists. Many subatomic particles were first discovered in cosmic ray interactions. The positron, the antimatter counterpart of the electron, was discovered in cosmic ray experiments in 1932. The muon was discovered in cosmic rays in 1936. The pion was discovered in cosmic rays in 1947. The kaon was discovered in cosmic rays around the same time. For decades, cosmic rays were the only window physicists had into the subatomic world at high energies. They were nature's own particle accelerator, delivering collisions at energies far beyond anything humans could produce in a laboratory. And here is something that drives home just how powerful these collisions are. The most advanced particle accelerator ever built by humans is the Large Hadron Collider at CERN near Geneva, Switzerland. The Large Hadron Collider accelerates protons to energies of about 6.8 trillion electron volts per beam. When two beams collide head-on, the total collision energy is about 13.6 trillion electron volts. That is an extraordinary achievement of engineering. The Large Hadron Collider is a circular tunnel 27 kilometers in circumference, lined with superconducting magnets cooled to temperatures colder than outer space. It took thousands of scientists and engineers over a decade to build and cost roughly $10 billion. It is arguably the most complex and expensive scientific instrument ever constructed. And the collision energy it produces, 13 trillion electron volts, is impressive by any standard. But the oh my god particle had an energy of about 300 million trillion electron volts. That is roughly 20 million times more energy than the Large Hadron Collider can produce. A single cosmic ray, a single proton flying through space, carried more energy than the most powerful particle accelerator humanity has ever built, and it did so by a factor of 20 million. Nature outperforms our best technology by an almost embarrassing margin. When a cosmic ray this energetic strikes an atomic nucleus, the collision creates a situation unlike anything that occurs naturally on Earth's surface. The energy is so concentrated, the impact so intense, that it recreates conditions that existed in the universe only fractions of a second after the Big Bang. At these energies, quarks and gluons, the fundamental constituents of protons and neutrons, are briefly liberated from their confinement. A tiny volume of space, smaller than an atomic nucleus, momentarily reaches temperatures and energy densities comparable to the primordial fireball that gave birth to the universe. And then, in a trillionth of a second, that tiny fireball cools and condenses into a spray of new particles that fly outward in every direction. Let's sit with this for a moment. A single proton, a particle you could find inside any hydrogen atom, has been accelerated to such an extreme speed that when it hits something, it briefly recreates the conditions of the early universe. That is not poetry. It is not metaphor. It is a literal physical fact. The energy density at the point of impact is comparable to what existed in the universe when it was less than a microsecond old. A cosmic ray impact is, in a very real sense, a tiny echo of the Big Bang itself, replayed in our atmosphere billions of times every day. Now, you might wonder how it is possible for something so small to carry so much energy. How can the universe allow a single proton to accumulate 50 joules of kinetic energy? Does that not violate some principle of physics? Does it not seem wrong somehow? The answer is no. It does not violate any known law. In fact, it is a direct and unavoidable consequence of the laws of physics as we understand them. The key is that there is no speed limit on kinetic energy. There is a speed limit on speed itself. Nothing can travel faster than the speed of light. But the speed of light is a limit on velocity, not on energy. As a particle approaches the speed of light, its energy increases without bound. You can always add more energy to a particle that is already moving at 99.9999% of light speed. That additional energy will not make the particle exceed light speed. Instead, it will manifest as an increase in the particle's momentum and its effective inertia. The particle gets harder to deflect, harder to stop, more damaging when it hits something. The energy goes somewhere. It just does not go into making the particle break the light speed barrier. This is a subtle but crucial point. In classical physics, there is a direct relationship between speed and energy. Double the speed, quadruple the energy. But in relativistic physics, that relationship changes near light speed. Energy keeps increasing, but speed does not. The extra energy goes into what physicists call relativistic mass, or more precisely, into the relativistic momentum and the total relativistic energy of the particle. The particle does not get heavier in the traditional sense. It still contains the same number of quarks. Its rest mass does not change, but it behaves as if it is getting heavier. It resists acceleration more and more. It takes more and more force to change its direction or slow it down. And when it hits something, it delivers more and more energy to the target. There is no upper limit to this process. You can keep adding energy forever. The speed will asymptotically approach the speed of light, getting closer and closer, but never reaching it. And the energy will climb higher and higher without any theoretical ceiling. The oh my god particle was traveling at a speed indistinguishable from light speed to any practical measurement. But it was not traveling at light speed. It was a hair's breadth below it. And that tiny, unmeasurable gap between its speed and the speed of light contained an enormous amount of potential for even more energy. If you could somehow add even more energy to the oh my god particle, it would not go faster. It would go from 99.99, 99, 99, 99, 99, 99, 99, 999, 99, 99, 999%. An increase in speed so tiny that no instrument could measure it. But the energy would increase dramatically. The universe does not set a maximum energy for particles. It only sets a maximum speed. This is what makes cosmic rays so fundamentally different from other things that arrive from space. Light from a distant star carries energy, but it is spread out over quadrillions of photons, each carrying a tiny amount. A meteoroid carries kinetic energy, but it is a large object with a correspondingly large mass. A cosmic ray is different from both. It takes an enormous amount of energy and concentrates it into the smallest possible package. A single particle, one proton, with more kinetic energy than a baseball. This concentration of energy in a single particle is what gives cosmic rays their unique destructive power at the atomic scale. When a cosmic ray hits an atomic nucleus, it does not distribute its energy gently across a large area. It dumps it all into a volume smaller than a trillionth of a centimeter. The energy density at the point of impact is beyond anything else in the natural world on Earth. Nothing in your experience, nothing in everyday physics, produces energy concentrations like this. Not lightning, not explosions, not even nuclear reactions inside a reactor. Only the collisions of cosmic rays with matter and the artificial collisions produced by particle accelerators reach these energy densities. And as we have already seen, cosmic rays win that comparison by a factor of millions. This is the deep truth about cosmic rays. They are not exotic or mysterious particles. They are ordinary protons. The same protons that make up your body, the same protons that make up the sun, the same protons that make up every star in the universe. What makes them extraordinary is purely and entirely their speed. Speed close enough to the speed of light that the rules of everyday physics no longer apply. Speed that transforms something negligible into something devastating. Speed that allows a particle weighing almost nothing to carry the energy of a thrown ball. Speed that can shatter atomic nuclei, create new particles from raw energy, and briefly recreate the conditions of the newborn universe. The physics is not mysterious. It is Einstein's relativity applied to its logical extreme. But the consequences are staggering, and nowhere are those consequences more visible than in what happens when one of these particles finally reaches Earth and slams into our atmosphere. The collision that follows is one of the most spectacular events in particle physics. A chain reaction that transforms a single invisible proton into a shower of billions of particles raining down from the sky. And that is where our story goes next. So picture this: a single proton, one particle, smaller than an atom, has been traveling through space for millions of years. Maybe it was launched from the expanding shockwave of a supernova remnant somewhere in the Milky Way. Maybe it was flung from the jet of a supermassive black hole in a distant galaxy. Maybe it was born in a gamma ray burst halfway across the observable universe. Whatever its origin, it has been crossing the void for an almost incomprehensible span of time. It has threaded through the magnetic fields of interstellar space, its path bending and curving with every encounter. It has dodged the faint photons of the cosmic microwave background, or perhaps lost some energy to them along the way. And now, after a journey that might have begun before complex life even existed on Earth, it arrives here. It reaches the edge of our atmosphere, and in a fraction of a second, everything changes. The proton crosses into the outermost fringes of the atmosphere more than 100 kilometers above the surface, moving at nearly the speed of light. Up there, the air is so thin that the proton passes through almost without noticing. It is traveling so fast that from its perspective, if you could somehow ride along with it, the entire thickness of Earth's atmosphere would be compressed by relativistic length contraction into a thin sheet only a few meters thick. But from our perspective on the ground, the atmosphere is 100 kilometers of gas, a substantial shield of nitrogen and oxygen molecules stacked above our heads. And as the proton plunges deeper, the air grows denser, and eventually its luck runs out. It is about to hit something. The collision happens high in the atmosphere, typically at an altitude of 15 to 25 kilometers. The cosmic ray proton strikes the nucleus of a nitrogen or oxygen atom. And this is not a gentle bump. This is a head-on nuclear collision at relativistic speed. The energy involved is enormous, far exceeding the binding energy that holds the target nucleus together. The nucleus does not survive intact, it is shattered. Protons and neutrons are ripped from the nucleus and sent flying. But that is only the very beginning of what happens. The energy of the cosmic ray is so great that the collision creates a burst of entirely new particles. Dozens, hundreds, or even thousands of particles are manufactured from the kinetic energy of the impact, conjured into existence through the conversion of energy into mass. The most common particles produced are pions. Pions come in three varieties: positive pions, negative pions, and neutral pions. All three are produced in abundance in the initial collision. Along with pions, the collision also produces kaons, which are heavier cousins of pions, as well as protons, neutrons, and other particles ripped from the shattered nucleus. This spray of particles erupting from the first collision is called the hadronic core of the cascade. Because hadrons is the term physicists use for particles made of quarks, which includes protons, neutrons, pions, and kaons. Now, each of these newly created particles is itself moving at very high speed, carrying a share of the original cosmic ray's energy. And each of these particles will itself collide with another atmospheric nucleus within a short distance. Those collisions produce more particles, more pions, more kaons, more protons and neutrons. Each generation of collisions multiplies the number of particles while dividing the energy among them. The total energy is conserved. It does not increase, but it gets split among more and more particles with each successive collision. This is a chain reaction, a cascade, an avalanche of particles multiplying as they descend through the atmosphere. Physicists call it an extensive air shower, and the name is apt. A single cosmic ray proton produces a shower of particles that spreads outward as it descends, forming a thin disk of particles wider and wider as it moves toward the ground, like an expanding pancake of subatomic debris rushing downward at nearly the speed of light. But the cascade is not just a simple multiplication of the same kinds of particles. It branches into distinct components, each with different characteristics and different fates. Let me walk through each one. The first branch is the hadronic core. This is the central spine of the shower, the line of successive nuclear collisions where the highest energy particles continue smashing into atmospheric nuclei, producing more hadrons. This core carries the bulk of the shower's energy and drives the cascade deeper into the atmosphere. Each collision in the core produces more pions, more kaons, and more nuclear fragments. The core is relatively narrow, concentrated along the axis of the original cosmic ray's trajectory. The second branch is the electromagnetic component. This is where neutral pions play a crucial role. Neutral pions are extremely unstable. They have a lifetime of only about 8.4 times 10 to the negative 17 seconds. That is 84 millionths of a trillionth of a second. Almost instantly after being created, a neutral pion decays into 2 gamma-ray photons. These are not cosmic ray particles. These are genuine rays, photons of electromagnetic radiation, carrying very high energy. Each gamma-ray photon then interacts with the electric field of an atmospheric nucleus and converts into a pair of particles, an electron, and a positron. This process is called pair production, and it is one of the most direct demonstrations of Einstein's mass-energy equivalence. A massless photon enters the electric field of a nucleus and emerges as 2 massive particles, an electron and its antimatter twin, the positron. The mass of these new particles comes directly from the energy of the photon. The electron and positron then radiate more gamma-ray photons as they are decelerated by interactions with atmospheric atoms, a process called Bremsstrahlung, which is German for breaking radiation. These new gamma-ray photons then produce more electron-positron pairs. Those electrons and positrons radiate more photons, and so on. The electromagnetic component of the shower is its own chain reaction, a cascade within a cascade. Photons producing pairs, producing photons, producing pairs, multiplying with each generation. This electromagnetic cascade is responsible for the majority of the particles in the shower. By the time the shower reaches its maximum development, the electromagnetic component can contain billions of electrons, positrons, and photons, vastly outnumbering the hadrons in the core. The third branch is the muon component, and this is the branch that reaches you. Among the particles produced in the hadronic collisions are charged pions. Unlike neutral pions, which decay almost instantly into photons, charged pions live slightly longer, about 26 nanoseconds. That is still incredibly brief by human standards. But at the speeds these pions are traveling, close to the speed of light, 26 nanoseconds is enough to travel several kilometers through the atmosphere before they decay. When a charged pion decays, it produces a muon and a neutrino. The muon is a heavier cousin of the electron, about 207 times more massive, and muons are remarkably penetrating. They do not interact strongly with matter the way protons and pions do. They do not produce electromagnetic cascades the way electrons and photons do. Muons mostly just fly straight through, losing energy gradually through ionization, but otherwise passing through matter almost undisturbed. Muons have a natural lifetime of about 2.2 microseconds. Even traveling at the speed of light, a muon should only cover about 660 meters in that time. Most muons are created at altitudes of 10 to 15 kilometers. They should decay long before reaching the surface. And yet, about 10,000 muons pass through every square meter of Earth's surface every minute. The reason they survive the journey is time dilation, the same relativistic effect we discussed earlier. Because the muons are moving at speeds very close to the speed of light, time passes more slowly for them from our perspective. Their internal clock runs slower. A muon that would live only 2.2 microseconds if it was sitting still in a laboratory lives much longer when it is hurtling through the atmosphere at 99.9% of light speed. From our reference frame on the ground, the muon's lifetime is stretched by its Lorentz factor, giving it enough time to traverse the full thickness of the atmosphere and reach the surface. This is not theoretical, it is directly measured. The detection of muons at ground level is one of the most straightforward and elegant confirmations of Einstein's special relativity. Without time dilation, the muons simply could not reach us. The fact that they do is proof that time itself is flexible, that it runs at different rates depending on how fast you are moving. So the complete picture of an extensive air shower looks like this. A single cosmic ray proton hits a nucleus high in the atmosphere. The collision produces a burst of hadrons, mostly pions and kaons. The neutral pions immediately decay into gamma-ray photons, launching an electromagnetic cascade of photons, electrons, and positrons that multiplies rapidly. The charged pions travel a short distance and decay into muons and neutrinos. The muons punch through the atmosphere, surviving the journey thanks to time dilation, and reach the ground. Meanwhile, the surviving hadrons in the core continue colliding with atmospheric nuclei, producing more pions and more kaons, feeding more particles into both the electromagnetic and muon branches. The shower expands as it descends, growing wider and wider. By the time it reaches the ground, the particle disk can be several kilometers across. A single cosmic ray, one proton, produces a footprint of secondary particles covering an area larger than a small city. The numbers involved are staggering. A cosmic ray with an energy of 10 to the 18 electron volts, a fairly energetic but not extreme cosmic ray, produces a shower containing roughly 1 billion secondary particles at its maximum development. The most energetic cosmic rays, those above 10 to the 20 electron volts, can produce showers containing over 100 billion particles. All of these particles, every single one, trace their existence back to a single proton that entered the atmosphere. One particle becomes 100 billion. This is the power of a cascade. This is what happens when enough energy is packed into a small enough package. Now, it is important to clearly distinguish cosmic rays from other things that arrive from space, because the terminology can be confusing. Cosmic rays are charged particles. They are physical matter, protons and atomic nuclei with mass and electric charge. They are deflected by magnetic fields. They interact with matter through the strong nuclear force. Gamma rays, despite the similar name, are something completely different. Gamma rays are photons. They are electromagnetic radiation, this same fundamental phenomenon as visible light or radio waves or X-rays, just at much higher energies and frequencies. Gamma rays have no mass. They carry no electric charge. They travel at exactly the speed of light. They are not deflected by magnetic fields. They interact with matter through electromagnetic forces, not the strong nuclear force. Both cosmic rays and gamma rays come from space. Both carry high energy. Both can be produced by the same violent astrophysical events. A supernova remnant that accelerates cosmic rays also produces gamma rays. An active galactic nucleus that launches cosmic ray particles also emits gamma ray photons. But the particles themselves are fundamentally different. A cosmic ray is a proton. A gamma ray is a photon. One has mass. The other does not. One is deflected by every magnetic field it encounters. The other travels in a perfectly straight line from source to observer. One interacts through the strong force, shattering nuclei on impact. The other interacts electromagnetically, producing electron-positron pairs or being absorbed by atoms. This distinction matters because it affects how we detect them and what we can learn from them. Gamma rays travel in straight lines, so when we detect a gamma ray from a particular direction, we know the source is in that direction. This makes gamma ray astronomy a powerful tool for mapping the high-energy universe. Cosmic rays, by contrast, are scrambled by magnetic fields during their journey. A cosmic ray that originated in a particular galaxy might arrive at Earth from a completely different direction, its original trajectory erased by millions of years of magnetic deflection. This is why identifying the specific sources of cosmic rays is so much harder than identifying the sources of gamma rays. Then there is ordinary background radiation, the kind you encounter in everyday life. This includes radiation from naturally radioactive elements in rocks and soil, radiation from medical X-rays, and radiation from radon gas that seeps out of the ground. This radiation consists mostly of alpha particles, beta particles, and gamma ray photons at relatively low energies. It is a fundamentally different phenomenon from cosmic rays. Ordinary background radiation comes from radioactive decay, a quantum mechanical process where unstable atomic nuclei shed energy by emitting particles. Cosmic rays come from astrophysical acceleration processes, violent events that boost particles to relativistic speeds. The energies involved are different by many orders of magnitude. A typical gamma ray from radioactive decay might carry 1,000,000 electron volts. A cosmic ray proton can carry 1 billion electron volts, 1,000,000,000,000 times more. They are related only in the sense that both involve energetic particles or photons. In every other respect, their origins, their energies, their behavior, and their effects, they are completely different phenomena. Now let's talk about protection. Because if cosmic rays are so energetic and so common, why are we not in danger? The answer is that we have two shields, and together they are remarkably effective. The first shield is Earth's magnetic field. Earth has a global magnetic field generated by the motion of molten iron in its core. This magnetic field extends far out into space, creating a protective bubble called the magnetosphere. Charged particles approaching Earth encounter this magnetic field and are deflected. Low-energy cosmic rays are particularly affected. The magnetic field bends their paths, steering many of them away from Earth entirely, diverting them toward the poles or deflecting them back out into space. Higher energy cosmic rays are harder to deflect because their greater momentum makes them more resistant to magnetic bending. The most energetic cosmic rays punch straight through the magnetic field with barely any deflection. But for the vast majority of cosmic rays, especially the very common low-energy ones, the magnetic field provides significant protection. The second shield is the atmosphere itself. Even for cosmic rays that make it past the magnetic field, the atmosphere acts as a thick absorber. As we have just described in detail, a cosmic ray entering the atmosphere triggers a cascade. The original particle's energy is distributed among billions of secondary particles. Most of these secondary particles are absorbed before they reach the ground. The electromagnetic component, the electrons, positrons, and photons, gets absorbed by the atmosphere. The hadrons in the core are absorbed by further nuclear collisions. Only the muons, which interact weakly with matter, and some neutrinos, which interact hardly at all, make it to the surface. The atmosphere is equivalent in shielding to about 10 meters of water, or about 1 meter of solid lead. It is a formidable barrier. Without it, the surface of Earth would be bathed in a much more intense radiation field. Cosmic rays would directly strike living cells at much higher rates, causing far more damage. This is why space is dangerous. Astronauts outside the protection of Earth's magnetic field and atmosphere are exposed to cosmic rays directly. On the International Space Station, which orbits within the magnetosphere but above the atmosphere, astronauts receive a radiation dose roughly 100 times higher than what people receive on the ground. On a mission to Mars, which would take astronauts outside the magnetosphere for months, cosmic ray exposure is one of the most serious health risks. A single heavy cosmic ray nucleus, an iron nucleus traveling at relativistic speed, can plow through human tissue, leaving a track of damaged cells in its wake. These heavy cosmic rays are rare, but over the course of a months-long or years-long mission, they accumulate. The long-term health effects include increased cancer risk, potential damage to the central nervous system, and other poorly understood consequences. Shielding spacecraft against cosmic rays is extremely difficult because the most energetic particles can punch through meters of material. And in some cases, adding shielding actually makes things worse, because when a cosmic ray hits the shielding material, it produces a secondary cascade inside the spacecraft, potentially creating more radiation than the original particle would have caused on its own. Solving the cosmic ray radiation problem for deep space travel is one of the major unsolved engineering challenges in human spaceflight. Electronics in space are also vulnerable. A cosmic ray or one of its secondary particles can strike a microchip and deposit enough charge to flip a bit in a computer's memory, changing a 0 to a 1 or vice versa. These are called single event upsets, and they happen regularly to satellites and spacecraft. Most of the time, error-correcting software catches and fixes these glitches, but occasionally, a single event upset causes a serious malfunction. In 2003, a voting machine in Belgium recorded an extra 4,096 votes for one candidate, an error that was later attributed to a single event upset caused by a cosmic ray. 4,096 is 2 to the 12th power. Exactly what you would expect if a cosmic ray flipped one bit in a binary counter. The error was caught because the total number of votes exceeded the number of registered voters. This is a vivid reminder that cosmic rays are not just an abstract astrophysical phenomenon. They interact with our technology and occasionally cause real-world problems. Given how extraordinary these air showers are, you might wonder how we actually detect them. After all, the particles in a shower are subatomic. You cannot see them. You cannot hear them. Each individual particle is far too small and too fast to observe directly with your eyes. And yet, physicists have built detectors that can reconstruct the entire shower from a single cosmic ray, tracing the cascade back to the original particle's energy, direction, and even its likely identity as a proton or heavier nucleus. The most impressive cosmic ray detector ever built is the Pierre Auger Observatory in Argentina. It covers an area of about 3,000 square kilometers, roughly 3/4 the size of the state of Rhode Island. That is not a typo. The detector spans 3,000 square kilometers of the pampas grassland near the city of Malargüe. It is the largest scientific instrument ever constructed by area. The reason it needs to be so large is that ultra-high energy cosmic rays are incredibly rare. At the highest energies, above 10 to the 19 electron volts, you might detect only one particle per square kilometer per year. To collect enough events to do meaningful science, you need to monitor a vast area. The observatory uses two complementary detection methods. The first is an array of 1,600 surface detectors spread across the landscape, each one a tank filled with 12,000 liters of ultra-pure water. When a charged particle from an air shower passes through the water, it travels faster than light moves through water. This does not violate the cosmic speed limit because light travels more slowly in water than in vacuum. When this happens, the particle emits a faint cone of blue light called Cherenkov radiation, similar to a sonic boom but with light instead of sound. The sensors inside the tank detect this flash. By recording when each tank is triggered and how much light it detects, physicists can reconstruct the size, shape, and direction of the air shower that triggered it. The second detection method is fluorescence. On clear dark nights, 27 telescopes at 4 sites around the perimeter watch the sky for faint ultraviolet light. When billions of charged particles in an air shower excite nitrogen molecules, those molecules emit faint ultraviolet fluorescence as they return to their ground state. The telescopes can actually see the shower develop in real time, a faint streak of light descending through the atmosphere like an ultraviolet meteor. By tracking the streak, physicists can measure the shower's development profile, how the number of particles grows and then diminishes as the shower descends. This profile tells them the energy of the original cosmic ray and gives clues about whether it was a proton or a heavier nucleus. Together, these two methods allow physicists to reconstruct individual cosmic ray events with remarkable precision. They can determine the energy of the original particle to within about 20%. They can determine the arrival direction to within about 1 degree. And they can make statistical statements about the composition of cosmic rays at the highest energies. The Pierre Auger Observatory has been operating since 2004 and has detected tens of thousands of ultra-high energy cosmic ray events. It has provided the strongest evidence for the GZK suppression, confirming that the number of cosmic rays drops off above the energy threshold, where interactions with the cosmic microwave background become significant. It has also found tantalizing hints that the highest energy cosmic rays might be coming preferentially from directions associated with nearby galaxies, though the evidence is not yet definitive. There is another haunting detail about cosmic rays and human beings that deserves mention. During the Apollo missions, astronauts traveling beyond the protection of Earth's magnetosphere reported something strange. When they closed their eyes to sleep, they saw flashes of light, brief, sudden streaks and spots appearing in their visual field even in total darkness. At first, this was puzzling. There was no light source, their eyes were closed. They were in a darkened spacecraft. But the flashes were real, and every crew that traveled beyond low Earth orbit reported them. The explanation is cosmic rays. A heavy cosmic ray nucleus, an iron or carbon or oxygen nucleus traveling at relativistic speed, can pass directly through the eyeball and interact with the retina, the light-sensitive layer at the back of the eye. As the particle traverses the retina, it deposits energy along its path, stimulating the photoreceptor cells exactly as light would. The brain interprets this stimulation as a flash of light because that is what the retina is designed to report. The astronauts were literally seeing cosmic rays. Their own eyes were acting as particle detectors, registering individual cosmic ray impacts as brief streaks of phantom light. This phenomenon was later confirmed in controlled experiments aboard Apollo 14, 15, 16, and 17, and it has been studied extensively on the International Space Station. Astronauts on the station report about one flash every 3 minutes on average, more frequently during passages through the South Atlantic anomaly, a region where Earth's magnetic field is unusually weak, and more cosmic rays can reach orbital altitudes. For future missions to Mars, cosmic ray exposure becomes an even more serious concern. A round trip to Mars would take roughly 2 to 3 years with current propulsion technology. During that time, astronauts would be outside the magnetosphere for months on end, fully exposed to the galactic cosmic ray background. Studies suggest that the cumulative radiation dose from cosmic rays during a Mars mission could increase an astronaut's lifetime cancer risk by roughly 5% or more. There are also concerns about effects on the central nervous system. Experiments on mice exposed to simulated cosmic ray environments have shown cognitive decline, increased anxiety, and impaired memory formation. The particles that concern researchers most are the heavy nuclei, the iron, silicon, and carbon nuclei that make up a small fraction of the cosmic ray population, but cause disproportionate biological damage, because they deposit so much energy along their tracks through tissue. A single iron nucleus at relativistic speed can punch completely through the human body, destroying every cell along its path, and leaving a narrow trail of devastation, the full thickness of whatever tissue it traverses. Over the course of a years-long Mars mission, an astronaut's brain would be traversed by thousands of these heavy nuclei, each one destroying a thin column of cells. The long-term effects of this cumulative damage are still poorly understood, and solving this problem remains one of the most critical challenges facing human exploration beyond the moon. So let's step back and take in the full picture. Every second of every day, cosmic rays are arriving at Earth from every direction. They have been traveling for millions of years, launched by the most violent events the universe produces. Supernova explosions that tear stars apart, jets from supermassive black holes that stretch for millions of light years, possibly gamma ray bursts that release more energy in seconds than the sun will produce in its entire lifetime. These particles cross the vast emptiness of interstellar and intergalactic space, deflected by magnetic fields, drained by encounters with the cosmic microwave background, until they reach us. They strike our atmosphere at speeds indistinguishable from the speed of light. Each one triggers a cascade, a chain reaction that converts one particle into billions. Those billions of secondary particles rain down through the atmosphere, most of them absorbed before reaching the ground. But some get through, muons mostly. About 10,000 of them pass through every square meter of Earth's surface every minute. Through the roof of your house, through your body, through the ground beneath your feet. Right now. Constantly. You cannot feel them. You will never notice them. But they are there. And they have always been there. For 4.5 billion years, this invisible rain has been falling. It was falling when the first living cells appeared in the primordial oceans. It was falling when the first fish crawled onto land. It was falling when the dinosaurs roamed the earth. It was falling when the first humans looked up at the night sky and wondered what the stars were. And it is falling right now, as you listen to these words. This rain has shaped us. Not dramatically, not in any way you could point to and say there, that is what cosmic rays did. But subtly, over billions of years, through the slow accumulation of mutations in DNA, through the slight ionization of the atmosphere that affects cloud formation and weather, through the constant background of radiation that has been part of Earth's environment since the planet formed, cosmic rays are woven into the fabric of our world. They are part of the environment that made us. And here is what I find most remarkable about all of this. The particles passing through you right now were accelerated by events of almost unimaginable violence. Somewhere in the universe, a star exploded, or a black hole swallowed a cloud of gas and launched jets of plasma at nearly the speed of light. Or two neutron stars collided in a cataclysm that shook the fabric of space-time itself. That violence, that raw cosmic fury, produced a particle. Just one particle. And that particle traveled for millions of years through the cold emptiness between stars, crossing distances so vast that the human mind cannot truly comprehend them. It survived the journey, it reached Earth, it hit our atmosphere and produced a cascade of billions of secondary particles. And one of those secondary particles, a muon born in the collision, flew through the atmosphere in a few microseconds, its life extended by time dilation, and passed through your body without you ever knowing. You are connected to the most violent events in the universe by an unbroken chain of cause and effect. The supernova that exploded 10,000 years ago and 10,000 light years away produced a proton that produced a pion, that produced a muon, that passed through your hand 5 seconds ago. You did not feel it. You could not see it. But it happened. That particle's journey from the heart of an exploding star to the palm of your hand is one of the most extraordinary stories in all of physics. And it is happening to you right now, thousands of times per minute, every minute of every day. The universe is not a quiet place. It is not a calm, gentle backdrop to human life. It is a seething, violent, energetic place where stars explode, black holes devour matter, and single particles are accelerated to energies that rival thrown baseballs. And all of that violence, all of that fury, echoes down to us in the form of an invisible, constant, silent rain of particles from the sky. Cosmic rays, misnamed, misunderstood, and almost entirely unnoticed, but always there, connecting us to the most extreme processes the universe can produce. The next time you step outside on a clear night and look up at the stars, remember this. The light from those stars is not the only thing reaching you. Mixed in with that light, invisible and undetectable by your senses, there are particles, protons and nuclei, stripped bare, carrying the fingerprint of some catastrophic event that happened long ago and far away. They're passing through you right now. They will pass through you tonight, tomorrow, every day, for the rest of your life. You are bathed in the fallout of cosmic violence. You always have been. And there is something strangely beautiful about that. Something humbling and awe-inspiring about knowing that the most violent events in the universe reach out across millions of light years and touch you personally, constantly, invisibly. You are, in the most literal sense, connected to the cosmos, not just by the atoms in your body that were forged in ancient stars, but by the particles that are raining down on you right now. Particles born in violence, traveling through the void, arriving at your doorstep after journeys of millions of years. That is what a cosmic ray really is. And that is why it hits with so much force, not because of what it is, but because of how fast it is going. Speed transforms the ordinary into the extraordinary. And the universe, it turns out, is very, very good at making things go fast. Thank you for joining me on this journey into the physics of cosmic rays. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the science that shapes our universe. And remember, right now, as you go about your evening, particles from exploded stars and the jets of distant black holes are passing through your body. You cannot feel them, but they are there. They have always been there, and they connect you to the most violent and extraordinary events the cosmos has ever produced. Good night, and may you never look at an empty sky the same way again.